Excellent. Hi, so thanks very much for the invitation, for the opportunity to speak here. It's really great to be here. I'm going to be talking about current work in the field of CMB lensing. And in particular, I'm going to discuss, first of all, the measurements. I'm going to talk about ongoing and upcoming work with Advanced ACT and Simon's Observatory and how we can use this to test Planck and go beyond Planck. The last part of my talk, I'll discuss some more very preliminary theory work, thinking about whether there might be room for improving how well we can probe small-scale CMB lensing. So first, let me give a brief introduction to this field. The CMB is really a unique source for the study of gravitational lensing because we understand it really well. We know exactly what redshift it comes from, and we really understand its statistical properties incredibly well. And beyond that, it's also unique in the sense that it lies behind nearly all the visible matter in our universe, or nearly all the sort of observable matter in our universe, including a bunch of dark matter. And so what happens as the CMB travels to us is illustrated here. The CMB is emitted from the last scattering surface and travels to the entire distribution of large-scale structure along the path to our telescopes. And this leads to a net remapping of the CMB sky that we observe today. In this remapping, you can describe fully with an observable the lensing deflection field, which points from the direction in which you receive a CMB photon to the direction in which it was originally emitted. Now, this lensing deflection field is a really interesting observable because it very cleanly, directly, and gravitationally, without the complications of bias, etc., probes the projected distribution of mass projected all the way from here with a broad kernel out to the last scattering surface, with the kernel peaks at around redshift 2. And so something we're going to be working towards over the next decade are really high precision maps of the gravitational lensing of the CMB. Very high fidelity over much of the sky. And indeed, these high precision lensing maps will actually underlie nearly all the key science, or much of the key science, of future CMB experiments. First of all, we will use lensing maps, these ultra-high precision lensing maps, to measure, or at least very tightly constrain, the sum of neutrino masses. And we've heard a lot about this from Mari's talk, how this works. Just to remind you, the more massive neutrinos are, the more the sort of fact that they're free streaming matters, and the more this suppresses the growth of small-scale structure. And the suppression or blurring shows up in a lensing map, which probes this in projection. And so in Advanced ACT and Simon's Observatory and SBT and CMB Stage 4, we're going to get increasingly good constraints to the neutrino mass. They're going to get, where we're getting to the point where we basically have to get detection, at least it's moderate significance. The second thing you can do, aside from probing neutrino mass and any other physics that changes how structure grows in our universe, is that you can take these maps of lensing and correlate them with galaxies and quasars to learn about biasing, or with weak lensing. And the latter is, I think, particularly promising because these sort of optical weak lensing measurements are one of our best windows to get dark energy, but they're very difficult. And so using these cross correlations, you can get checks for systematics and potentially even self-calibration that could really improve constraints. But finally, lensing is not just a signal that's really cool because it probes how structure grows and what structure looks like, but it's also a problem. And if you're interested in the early universe, which I think a lot of people here are, lensing is also a problem for you. Because this lensing makes B-mode polarization, and these lensing B-modes act as cosmic variance noise, as Anthony mentioned, that can obscure a small inflationary B-mode signal and limit the constraints. And so the final reason why you want to make a map of lensing, why you want to measure high precision lensing maps, is because you want to remove the lensing. You want to de-lens and reveal a small level of inflationary B-mode polarization if it's present underneath all that lensing noise. This is going to be really important for CMB Stage 4. Okay, so having motivated, hopefully, why we want to measure these high precision lensing maps, how does this work? How can we measure the lensing? Well, what we actually do right now is we measure a quadratic estimator. We look at new lensing-induced correlations between two different formerly independent modes of the CMB temperature and polarization with some weight. Now, I've always found this to be not particularly physically intuitive, so you can show, though, that in some limit at least, this reduces to a very nice physical picture. And the physical picture is that this estimator is just locally measuring the power spectrum, the 2D power spectrum in Lx and Ly. And this power spectrum is affected by lensing. The CMB is magnified, then the power spectrum also gets kind of compressed and stretched. And if it's sheared, the same thing happens to the power spectrum. So by looking at the local stretching and shearing of the power spectrum, you can figure out the lensing and make a map of the lensing. And if you're used to galaxy lensing, it's almost exactly the same. The analogy of a galaxy shape is the shape of the CMB correlation function. Now, these kinds of measurements have already made a ton of progress in the last decade, where we just made the first detections, to now where we're actually quite high precision cosmology, and that's really expected to continue. And the reason for this is that this is really driven by a really fantastic advance in the CMB experiment performance and noise level. So you can see there's almost an exponential decrease in CMB experiment noise level that we've seen so far, and this is really expected to continue from Planck to the next generations of ground-based CMB experiments, such as ACT, ACT-Pol, SVDP-Pol, Advanced ACT, Simon's Observatory, and then CMB Stage 4. So we have a lot of exciting ground-based CMB to look forward to that's going to go further down the sort of exponential improvement in noise. And so now, let me step back a little bit and talk a little bit about some recent work on the ACT experiment, in particular on ACT-Pol, the polarization-sensitive receiver that's been mounted to the ACT telescope. Here you can see ACT. This is actually the ground screen. Here's the actual telescope and the mirror. Photons go in, bounce around, end up on a big array of very sensitive transition edge sensing bolometers. And these kinds of experiments are great because they allow us to make very high resolution maps of the CMB temperature and polarization. And this is really good for making lensing maps, right? So you can make really nice maps of the lensing of the CMB that actually tell you about how much structure there is in a certain direction. And this is something, but of course, if you want to describe this statistically, what you have to do is measure a power spectrum of lensing, the lensing power spectrum that tells you how much lensing you have as a function of the angular extent of the lens. This is something we did for the first time back in 2011. We've gotten quite a bit better at it now. So now let me show you some early ACT-Pol lensing results based on only 10% of our data. So this is very much sort of showing our method and almost sort of science verification type. But even with 10% of our data, we can get, I think, a very nice lensing power spectrum is shown here in red. The amplitude is consistent with Planck, actually a little bit higher, but very much consistent. This is quite a clean measurement. We spent a lot of time working on systematics, but going forward, the main thing to think about is that there's sort of few percent level biases from foregrounds. But I'm pretty optimistic that with more frequencies and new estimators, we'll be able to solve that. So even though this is just an early result with a small fraction of our data, you can actually get some nice constraints on cosmological parameters, such as the neutrino mass. So here you can see a constraint on the sum of neutrino masses, less than 400 millielectron volts at 2 sigma, so it's something like a factor of 2 less than Planck. But all experiments are really closing in on this lower limit where we have to detect something. You can also show this as a constraint on the amplitude of structure and a sort of degeneracy contour with sigma 8 and omega matter. You can trade one off for the other to give the same lensing. Again, this is sort of comparable to a sort of science verification type data set, but that's about to change. And the reason for that is that this data that I've showed now is based on what's shown here in orange, a small fraction of what we have in the CAM through 2016. And we're analyzing that right now, and I think it's going to be really fun and really exciting for lensing. So now let me show you some preliminary maps. First of all, the CMB. This was made, I think, an hour ago. There's a lot of atmosphere, but still, the point is that we're really mapping 12,000, this is a map of 12,000 square degrees of temperature and polarization over, the sky area that's shown here in red, sort of up here. The noise level varies quite a lot, from more than 30 to below 10. And we're analyzing this now. And so just to show this, I'll show you a lensing map from here. I mean, this is very, very early days, but I just want to make the point that this is something we're working on right now. So you'll see, there's some weighting features here that are due to the mass. It's very preliminary, but we're doing it now. We have 12,000 square degrees compared to 500 for the first release, and we're working very hard to get this out. And I think that's really exciting because Planck has already gotten really precise in lensing power spectra and has given us really great cosmological parameters. But with this data set that we have right now, with the data that we have right now, I think we really should be in the ballpark that we should potentially be able to independently check the cosmological parameters from Planck, and in particular, the lensing power spectrum from Planck. And potentially, if you combine action Planck maps and reconstruct lensing on those, you might be able to go beyond Planck. So we're working very hard on analyzing this. It's quite challenging because it's a large data set, very high resolution, a lot of dynamic range in terms of the noise. So, but we're working at it, and we expect to get a nice power spectrum and a good constraint on neutrino masses. So stay tuned for that very soon. But in the near future, around 2020 and beyond, we have even more exciting experimental work coming. So already funded is the Simons Observatory, which is going to build up a big array of CMB telescopes in the Atacama Desert, and ultimately will contribute to the ultimate ground-based CMB experiment, CMB Stage 4. And if you look at these future ground-based CMB experiments and just do forecasts, they're incredibly promising for lensing, right? I mean, if you just do a forecast, for example, for Simons Observatory, you definitely get sub-percent lensing power spectra. So this is going to very soon become incredibly precise. And so any physics that changes how structure grows at all, over a broad range of redshifts, will show up in this lensing power spectrum. So for example, neutrino masses, even in the most pessimistic scenario, you'll detect sort of at moderate significance. So we can expect an error of around 20 to 30 millielectron volts, depending on what the optical depth is. So obviously, these are forecasts, and there's a lot of work we have to do in order to realize these, both in theory and analysis and systematics control. But I think there's actually also some potential for new work, thinking about new things to do with the CMB data sets that are getting really good, really signal-dominated, really low noise. And I'll just give show some extremely preliminary work in the last 2 minutes of my talk on one such idea. So the idea is really to ask how much better we can do on small scales in the CMB lensing. And this is sort of motivated a little bit by a puzzle, which is, on the one hand, the following. If you look at the standard quadratic estimator for CMB Stage 4, even for a futuristic experiment, and you look at the noise, compared to the signal, this noise just blows up at high L for small lenses. So you look at this plot, and you might conclude there is no way I can ever probe very small scales in the lensing, and no way I can ever probe very small scales in the matter power spectrum. Which is too bad, because those scales are really interesting for things like warm dark matter and axions, and individual halos like clusters. So it seems to say that doesn't work. But on the other hand, if you just do the dumbest possible thing, and you don't try to do any fancy lensing reconstruction or anything, and you just plot the CMB temperature power spectrum to a high enough L, you'll see that you can basically just read off from the high L temperature power spectrum, if you neglect some complications with foregrounds, you can basically just read off the lensing power spectrum for, say, CMB Stage 4 noise. So how is that possible then? On the one hand, this fancy lensing reconstruction, just the noise blows up. On the other hand, I don't do anything. I just measure the power spectrum of the temperature, and I can see it at L of 5,000, 6,000. But the reason I think this is going on is that this quadratic estimator is getting very far from the true maximum likelihood, and there are better estimators out there, and I think we can do a lot better out here on small scales in the lensing. And so to motivate this a little bit physically, you can sort of understand why the quadratic estimator, which is basically all people have done in data so far, fails so badly. Because the small scale CMB gets incredibly simple. If you look at the small scale CMB, it just looks like a gradient, the primary CMB. When you have lensing on top of it, a lens will kind of produce a dipole according to this equation. Now, what the quadratic estimator does is it takes these small scale fluctuations, multiplies them by another power of temperature to get a quadratic, but that means you have a sort of square of this long wavelength gradient. And so you have the square, you have cosmic variance from the long wavelength gradient. You're averaging over all possible gradients, and so you're always cosmic variance limited. So this quadratic estimator is never going to get really good, no matter how small your noise gets. But the thing is, you can just look at this and do something incredibly simple and say, I know I can measure the small scales, I can measure the long wavelength gradient, but I'm going to basically just divide them by the actual realization of the gradient in my patch. And that basically gets rid of this cosmic variance. And this is a really old idea, but we've actually just revisited this again, first of all for the context of clusters, because we're starting to look at these future experiments that will have such low noise, that these kinds of cosmic variance considerations really matter. And so we first applied this to clusters with sort of a matched filter procedure. Ben, a really good grad student, and Simona Ferraro have worked on this with me. And you can see that for small clusters that are far away, where these sort of high resolution matters, you get a significant improvement over the quadratic estimator. And it basically looks to be pretty much as good as the maximum likelihood estimator. But I think something that we're working on right now, this is very much work in progress, but I think it would be really cool if this actually works out, is, I think there definitely is potential, given the arguments that I've presented earlier, that we can do a lot better on the small scales in the lensing power spectrum with this upcoming high precision, low noise data. And so, this is really work in progress. We're trying to extend this kind of gradient inversion method, or also, it's another path to basically try to implement the maximum likelihood in this limit. And so, stay tuned on how well this works, but it would be really cool if we could use this to measure really small scale lensing and very, probe warm dark matter and axion-like particles really well. So stay tuned on that. I hope I convinced you that, first of all, CMB lensing is important because it underlies our constraints on inflation and dark energy and neutrino masses from future CMB. We've already made a lot of progress, but soon with advanced app, Simon's Observatory, and then CMB Stage 4, we'll be able to check and then go beyond Planck. And that might open up some new opportunities. So, thanks.